Sorry, my voice isn't quite there. I'm on week 3 of the same cold that I just can't seem to shake. You get that? Anyone else sick? No one else? All right. Yeah, cough drop, anyone? So I'll apologize if I start hacking during class, but I'm just as prepared as I can be. I looked at your homeworks just this morning, and not everybody is done yet, so I can't go over the answers. So as soon as everyone has finished, I will be able to go over that. If you see any problems, or if you're not sure why you got something wrong, let me know. What you should see is if you got an answer correct, it's green. And if you got an answer wrong, it should be red followed by the correct answer in green, so you can see what it should have been. So let me know immediately if there is anything that I need to check on, or if you have questions about that. In terms of the schedule, next week you'll have another quiz due in Icon. That's not ready yet. I wanted to see how far we get this week. I'll put it up probably on Thursday after class so that you'll have the weekend through Monday to work on it. It'll be just another 4 questions. No grades, just grading for effort. And then homework 2 will be the following week. It looks like that one is going to be another one on interactions, because we won't have a chance to get very far into nested data before it's time to do that. I will let you know when that one is ready. It should be later this week. But now the moment we've all been waiting for, 2-level data analysis, now that you've gotten all of the prerequisite material out of the way and fresh in your mind, so we can get to the fun stuff. Are you ready? Yes, heck yes. Yay, exactly. So from single level to multi-level, that's where we are headed first. Talking about fixed effects only first, and then adding random slopes as well in our next unit. So just to remember, vocabulary. 2 sides of any model. Model for the means versus model for the variance. So what we've been focusing on is the model for the means, the idea of the fixed effects of the model, how the predictors combine to be able to create an expected outcome. Now what we're changing our focus to is our friend E that has sat here ignored most of the time, the model for the variance. At one point in time, you were told that you had to assume certain things about E, right? If you're fitting a model that looks like this, then your assumptions are that E is normally distributed, has constant variance, and is independent. If those things aren't true, you need a new model. And so the model fix that we're going to look at then is the idea of how do we change the model for the variance to be more suitable for data that have multiple dimensions of sampling. So just to remind you some words that you'll see periodically here, you know what they are. Variance, right? How far off from the mean observations are in squared metric, standard deviation being the square root of that, how far off on average. Covariance is association in unstandardized terms. So we'll look at variance covariance matrices here before too long that describe associations amongst persons and classes. And then correlation being the standardized version of these, such as intraclass correlation, one of the first things we get to talk about. So we started here in single level model land, right? Empty model. No predictors. If we have a single level model, then we start off with our best guess for any observation is just the grand mean. And how far off from that grand mean each observation is the definition of variance. But what if I said that that distribution actually came from 3 distinct groups with 5 people each? So we've got the blue group, the yellow group, and the purple group. How would our empty model need to change? Well, start with the same idea. If I don't know anything else about a person, my best guess for their outcome is still the grand mean. However, in this case, I do know something else about a person. I know from which group they came. So rather than guessing a naive grand mean as the best guess, why don't we start at the group mean? This idea of changing the default place becomes the basis of what is going to be called a random intercept. So fixed effects, which we've had in regression, intercepts and slopes, the word fixed means everybody gets the same. The word random means in this class, each group gets their own. It's the highest level of sampling that gets their own. In this context, each group is going to have their own intercept in the model. So in allowing each group to have their own intercept, what we're actually doing is partitioning total variance and an outcome immediately into two sources. So the difference between the group means here, given by the dashed lines and the red line, how far off each group mean is from the grand mean, that becomes the basis of between-group variance, and that is what we refer to as inter-group differences. Within a group, we have variation of each individual person relative to their group mean. So within a group here, that is within-group variance across the people from the same group, or intra-group variability. So the total variability hasn't changed, it's just been attributed to two different sources. How much of it is between group means, and how much of it is within people, within groups across people. So let's say that I have a plot here of persons within groups. So this would just be a count, person 1, 2, 3, 4, 5 within each group. And on average, you wouldn't expect any differences across people necessarily. And the black line is the average for the sample, and each of these individual lines is the average for one group, or is data from one group. So if I had fit the previous model to this type of data set, and focusing on, say, the purple group here specifically, my conceptualization of the E term would have to include all of the variance. So the difference between all of the means for the first person across groups and the first person from my group is here, 2, 3, 4, 5. But these E's are related to each other. They're all below the line. That's not supposed to happen. E's are supposed to be independent. So we fix it by giving a new reference point for defining the E variance. So what we've done is add a new term. This is our new friend U. U0, specifically, this is a random intercept. Each group gets one of these, which is why it has a G subscript. So this U0 is for group G, which is the purple line here. It is how far off the group's mean is from the grand mean. So that is our new reference point. Relative to that new group mean given by the dashed line, E becomes how far off is each person from that line within group variation. So the total distance from the grand mean line to each data point is the same, it's just been partitioned into two different sources. Two different error terms, if you will. So what we've done is capture the correlation between the E's with this U term. After we partial out the fact that all of these people are below the mean because their group is below the mean, relative to that group mean, the E's are supposed to be independent. So the model then stipulates that we do have dependency. It's dependency of a specific source, a group mean difference, and therefore operates constantly across all the people from the same group. So it looks like this when you put it back together. Our new MD model has two different kinds of variability. We have how far off each group is from the grand mean. So the grand mean is the mean of the group means at this point. That's level 2 variance. It's variance across the U random intercepts specifically. By convention, in my textbook and in every other one, level 2 variances are given tau squared as notation. I always put a subscript as to what it is the variance of. So the variance across groups in these group mean deviations is given by tau squared sub U0. So this is intergroup level 2 variation between groups. Within a group then, around the group mean lines is level 1 residual variance, the E's, and it's sigma squared E, just like in regression. So differences between people still given by E, we've just added another level here to account for differences between groups as well. So then E changes to become group-specific intra-group variance. Okay, how are we doing? So in equations, switching notation into a multi-level style. GLM empty model, everything goes on one line, no predictors, one source of variance. Y gets an I subscript because it's for each individual. E gets an I subscript because it's for each individual. And beta 0 did not have an I because it's a fixed effect. Everybody got the same. Now I'm switching to writing out y, and I have decided to buck tradition here. And instead of going ij, which means nothing, I'm going PG because person in group. Why not? So y for each person within a group is a function of a new beta 0, which is group specific. In this slide and the ones that follow, terms that go with the model for the means are red, and terms that go with the model for the variance are blue. And there's a reason why this beta 0g is still black. This is not a parameter. It is a placeholder for other parameters. It shows up as an outcome then at level 2. So beta 0g is the group specific intercept. It comes from a linear combination. So this new y-looking thing, this is gamma. This is a fixed effect. This is the fixed intercept specifically. So gamma 0, 0, in this model, because we have no predictors, it's going to be the grand mean of the group means. U0g then is how far off each group's mean is from that grand mean. So if I'm from the purple group where my group is below average, my U0 would be negative. If I'm from one of the groups that are doing better than average, my U0 would be positive. The mean of the U0s is this gamma 00. So beta 0g is a new random variable with a mean of gamma 00 and variance given by tau squared. This U0 is the idea of variability in the same way that E is the idea of variability in a regression model. After allowing each group to get its own intercept, we then pick up E at level 1, which is the remaining difference between the group's predicted mean and the outcome for each individual person. So if I were to forego this more complicated multi-level notation and just write it as 1, substituting in for the beta 0, it looks like this composite right here, where the term in parentheses is what was given by beta 0g. So gamma 0, 0 is my reference point, grand mean of the group means. Add to it how far off my group's mean is from that grand mean. Then once I'm at my group's mean, how far off am I relative to the rest of my group? Question?
I'm a little confused. This y or is that new reference that you give to the group in the slide before that you
This one?
Yes,
Mm-hmm.
it's
The dotted line is the new reference.
Okay.
Yeah. Mm-hmm. Exactly. Yeah. Okay. So at this point, we have not explained any variance. The concept of R squared does not make sense here. All we have done is say that we have unknown variance, but it's for 2 different unknown types. U0 variance is why are some groups higher on average than others. E variance is why are some people in the group higher than the rest of their group. Both of these are equally error terms in the sense that we don't know why the variability is there. We just know that it is attributable to different sources. So when you have clustered data, this is the bare minimum that you would expect in terms of variability. Differences across groups, differences across people. Other questions? Okay, so a logical question then is, well, how much do you have of each? And that's the very first thing you'd want to figure out, which is what's known as intraclass correlation. So intraclass correlations more generally are ratios of variances. This one in particular has a very well-known form. It's the between-group variance conveyed by the random intercept variance over the total. So between-group due to random intercept plus residual. So I've written this 3 different equivalent ways. If you prefer words, symbols, or ideas, take your pick. So you can think of the ICC in either of these 2 ways. It's complementary, both are correct. The easiest way to think about it, perhaps, is that it is the proportion of total variation that is between groups, that is due to group mean differences specifically. Alternatively, you can think of it as the average correlation of people from the same group. ICC ranges from 0 to 1, where 1 would mean all between group differences. So the people in the group are identical. 0 would mean no group mean differences. It really is an independent random sample. Somewhere between the two is where your data are likely to lie. In grouped data, intraclass correlations tend to be lower, less than maybe 0.2-ish. In other types of dependent data, like longitudinal data, where times are nested in groups, ICCs tend to be much higher. So it just depends on the type of nesting that you have as to what this can expect. So sometimes folks have a hard time wrapping their head around the second definition because it's the average correlation within groups, yet the numerator is between groups. So I wanted to give you a sense of what that means. So this is the picture that I had before. If this is what your data look like, this would describe a relatively large intraclass correlation because the differences between the group means are large relative to the differences within the groups. So if you think about correlation as prediction, right? Like if I gave you one of my purple data points here, and I said, what's your best guess for someone else from the same group? If you have a strong intraclass correlation, your guess would be really good. You'd be able to predict what one person's data point looks like from anyone else in that same data set, in that same group. A high intraclass correlation means people are really similar, groups are really different. In contrast, a picture like this would show a smaller intraclass correlation. Now, people are variable and the groups are not that different from each other. If I gave you one person's data point from the purple group and asked you to predict someone else's, it's much harder to do that reliably because variance within the group is so big. So this would be a small intraclass correlation, a small amount of variance that's related to group mean differences in the outcome. Okay. How are we doing? Is this new stuff or old stuff? New? Good, it's supposed to be.
So actually, it's kind of like very similar to one-way ANOVA, like using one-way ANOVA on the second level.
This is a random effect ANOVA. Absolutely it is.
Is that?
Yeah, you are absolutely right.
Okay.
The difference is whether or not you have to pay attention to different group sizes. So I think traditional least squares requires balanced groups or otherwise gets bogged down by that, whereas residual maximum likelihood that we're going to be using is not really a problem. So yeah, this is another way of thinking about this. This is a random effect ANOVA, where group is the random factor.
Also, like because you mentioned about different sample size, so like when you go back, when you use like a grand mean, like if like each group has a quite different number of samples like within a class, would you like adjust? Or like just take like a very simple like grand mean based on like each group's mean?
Depends on the model. So let me back up for a second and answer that question. This right here. So if you fit a model for grouped data, two-level data, where you don't have this random intercept, then the grand mean given by the fixed intercept is just the pooled mean, like you dump all the data points together and find the mean. Whereas once you put this random intercept in, this is the mean of the group means, where they're equally weighted. And so this becomes a different number if you have a different number of individuals contributing to each group. And the inference is different as well. So yeah, it depends on the model, and the same thing will be true of the slopes, by the way. When you have a fixed slope, it's based on the pooled data. When you have a random slope, which is heading next, then it's the mean slope of the group-specific slopes. Sure. Other thoughts, questions? Okay. So there's two ways of thinking about intraclass correlation. If you're into multi-level research, right, you really want to look at differences between schools and differences between kids, or differences between countries and differences between respondents, right? This is cool. If what you really care about are students and you just happen to have to get them from multiple schools, this is a problem. Same phenomenon, different interpretation. This idea of dependency. So one of the things that you can use intraclass correlation for is power analysis in clustered samples. Intraclass correlation contributes to something that is known as a design effect. The formal definition of this is given here as the ratio of the variance using a given sampling design to the variance using a simple random sample from the same population given the same total sample size either way. Less formally, the design effect is how screwed you are by getting a clustered sample for your power. That's the easiest way to think about it, because that's what happens. It is a function of the intraclass correlation for individuals from the same group, as well as the number of individuals per group. So it's 1 plus the group sample size, number of level 1 units here, times the intraclass correlation gives you your design effect. N effective then is what your actual sample size is in terms of power, number of total observations divided by the design effect. So if we work this out, only when you have 1 person per group, in which case n minus 1 is 0, and you wipe this out, then your design effect is 1, and the total number of observations is your effective sample size. So if you have 1 person per group, or your group intraclass correlation is exactly 0, and this drops out. Only in those 2 cases is your total number of observations the same as your effective number of observations. Otherwise, it's going to be somewhere between your level 1 sample size, the total, and the number of groups. So if you are in the case where your interclass correlation is 1, everybody in the group is exactly the same as each other, like they're automatons, then your number of people is your number of groups, effectively. And your power to detect person-level effects is your number of groups. So somewhere between people are actually independent, my total is my total, or people are exactly the same, my total is my number of groups, you're somewhere between the two in terms of your effective sample size. And this is one of the reasons why you cannot ignore an intraclass correlation no matter how small, is because it depends on the number in your group how big of a problem it becomes in introducing dependency into your data. So here's a couple examples. Let's say that I sample 5 patients from each of 100 doctors, so not so many. Intraclass correlation of 0.3. So in that instance, 30% of my variation in my patient level outcome has to do with which doctor they go to. 70% is between patients within doctors. That gives me a patient design effect of 1 plus the number of patients minus 1, which is 4 times the interclass correlation, is 2.2. So even though I ostensibly have 500 patients, divided by the design effect gives me an effective sample size of 227. That means that I actually have the power at level 1 of 227, even though I have 500 patients. $20 students from each of 50 schools and an interclass correlation of 0.05. So this is pretty typical. Small interclass correlations for school level phenomena. The student design effect here works out to be 1.95, almost a design effect of almost 2. So your sample size is effectively halved. So in practical terms, if you knew that you needed 513 people according to your power analysis to have enough power to do what you wanted to do, and this was the way you were getting your sample, you need to go out and get 1,000 people to get enough effective people to be able to do what you want to do. So I don't see design effects calculated for many other reasons besides study planning. So if you have a reasonable guess as to what your range of intraclass correlations are likely to be, and you know what your sample design is going to be in terms of number of people per group, then you can forecast what your design effect is going to be, and thus how many extra people you need to sample to overcome it. One other way that you can overcome it, though, is to reduce your interclass correlation. How do you reduce group level variance? Group level covariance. So intraclass correlation is still referring to error terms after we put predictors in the model. Hopefully this may be smaller if you have successfully accounted for all the reasons why your groups may have been different. So one question that I get periodically, if my intraclass correlation is non-significant, let's say it's like 0.001 or something, do I really need to do a multi-level analysis? Yes, the answer is always yes. The design effect depends on sample size, not just ICC, but beyond that, the intraclass correlation can increase after you add predictors. What we will see in some of our first examples is that so the after predictors or conditional version of the ICC can be much higher, even if it's initially 0. So for that reason, you need to worry about maintaining a distinction in your levels, having a random intercept variance in a 2-level model, and also because of the potential for contextual effects of level 1 predictors. That's something we'll talk about, I think, Thursday. We'll get to that. So, always multi-level. Only if you get all the way through everything that you're doing and there is never a random intercept variance that's ever present, would it be okay to ignore it. Yeah?
Does that still apply if you choose to just do like dummy variables for all the schools or something like
No, because then you have removed the intraclass correlation by including those dummy variables for school as a fixed effect. So you have done that instead of add school as a random effect, and that is totally fine. The only thing to keep in mind is that when you've controlled for school with those dummy variables, what you have done when you enter them as a main effect is control for intercept effect of school. If you want to control for school on slopes, then you would need to interact each of those dummy variables with whatever person level predictors you're interested in. So, good questions. Yeah.
I have 2 questions. The first one, when you talk about the N, which was, I think on slide 15.
Yep.
So when you talk about the number of levels, units, so according to you, the ICC can be large if you have a larger group size, and then otherwise it will be down because you have smaller groups and more people regardless, even the sample size is the same.
Mm-hmm.
So here, for the number of level 1 units, do you have any kind of reference? How much would you have? Because on the next slide, you have the same number of the total people of 1,000, I think. So, but the first one, you have 20 by, so how is that? Because which one would you recommend? So, because for the multi-level modeling, we're supposed to have more groups with a smaller number of people in each group in order to get a larger ICC. So do you have any reference number for the N at level 1 unit? Because for the next slide of 16, you have the same total of 20 by 50. Another is a 5. It's kind of. So what if I have the same number of people, but you have 2 different types of design?
Mm-hmm.
So in order to get a larger ICC, you're supposed to have more groups?
A larger ICC would be, it's not related to group size. A larger design effect is related to the number of people within a group. So the design effect is created by large ICC.
The next slide of 16, you have 5 patients,
Mm-hmm.
and the next one you have 20. So, but I didn't, but this one is more though, this one, right? But I didn't calculate the ICC.
Yeah, these are two wildly different
Yeah,
ICCs.
I know it's different, but according to the number of patients, so it doesn't matter because you have 100 doctors, which is the second level class, so we'll have a higher ICC. So my question is that, so if you have 5 patients, 100 doctor, or on the other hand, you have 10 doctor, 10 patients, 5 doctor, what is that? 10 and 50,
Mhm.
So the total is the same. So which one do you prefer?
Ah, yes. There is no right answer. Depends on which effects in your model that you want to be most concerned about powering. There is a piece of software called Optimal Design that's free. It's Radenbush and his colleagues that have made it, and they have scenarios plugged in where you can answer that very question. If you have budgetary constraints and it costs, X amount of dollars to add an extra person and it counts Y amount of dollars to add an extra school, like where the trade-off is, you can start to answer your questions based on what would be relatively more efficient to add more schools or more students in this case. In general, if you want to have power for group level predictors, you need more groups. If you want to have power for person level predictors, you need more persons. But then the hard part comes in when you have cross-level interactions, which is when you want to be able to examine group differences in person-level predictors, the effects of person-level predictors, in which case you kind of need both. So there's not one ready solution that works for all situations.
So then come back to the slide 15. So when you talk about the level 1 units, so there's no concrete answer. For example, it can be as minimum as 1.
So I'm just saying that in terms of if you had one person per group, that is the optimal way to avoid a design effect. But then you can't look at anything related to people, only groups, right? But that would be a terrible idea from the perspective of, are you going to let one person represent a whole group?
Just extreme example.
Yeah.
I don't mean that.
Mm-hmm.
Or on the other hand, you have a...
Mm-hmm. The idea is that if you have a whole lot of level 1 units, a whole lot of people, it's not necessarily a whole lot of people. It really depends on how they're grouped and how related they are within groups.
But in the real world, so when this is about design, but in the real world, when you collect the data, I don't think it's possible for you to get the same amount of the persons in each group to do. So, for example, especially in an educational kind of a setting.
Yes. So you would have to figure out some way of adjusting the design effect for unbalancing groups. One thing you could do is like a weighted analysis, where if you calculated a design effect for however many groups of each different sample size and then pooled them all together, you could do something like that. I think in your textbook, Snyder's and Bosker has a suggestion for how to deal with unbalanced sample sizes. But yeah, I mean, I think you could use this as the average level 1 sample size. It would be an approximation, or you could do something that's more specific. But the idea is just that having more people in a group makes it harder to have a greater effective sample size. That's just sort of the general perspective. Mm-hmm. All right, where were we? This one. Yeah. So your question, Hansi, you get it right? Yes. I was doing worse than the other class did. Well, I got 1. So yes, 2 ways of addressing group differences: fixed effects or random effects. We talked about this on the first day of class, 5 weeks ago. So if you don't care about your groups, you just need to control for them, or you don't have that many and therefore you can't possibly care because you don't have any power to detect differences across them, fixed effects is perfectly fine. So that's where you would put in literally group ID as a categorical predictor, and group goes out of the model, and then you have people who are independent after controlling for group as a fixed effect. If you have less than 10-ish is sort of the conventional wisdom, but I would argue anytime that you either want to make inferences about your groups that are specific to that group, or you don't have any intention of looking at group level predictors, you can do this. There are clustered corrected standard errors you can come out of various programs like Stata. What's it called in Stata, folks? There's like a clustered sample something or another. No? You remember? I don't know what it's called, but I know they have it. Yeah, I think that's what yeah. So that's analogous to this without you physically having to put the fixed effects in. They basically take the residuals and calculate the group mean differences and take them out of the residuals and then make the standard errors. The same thing you can do in M+. There's a clustered sample correction. The idea is just sort of like, I don't care about it. I just want to control for it and make it go away. Versus putting group in as a random effect then allows you to quantify group differences and predict them with group level information. So you got to care one way or the other. Which way you choose depends on what you want to do next. All right. Can I tell you a true story? So there was once a job talk at a university where I worked, and I'll not say which one since there's been several. This person is now not only hired but promoted at this university. Gave a job talk involving a sample of children nested in classrooms and in schools. And in her job talk, she stated that they tested a whole bunch of classroom level predictors and a whole bunch of school level predictors and didn't find any that were significant, and therefore they decided just to do a regression. Cool or not cool? Not cool. Why not? What do you think?
It's probably washing out variances.
Washing out what?
Because it can vary across schools. Would that happen? I don't know. In my head. So if like one school has an effect, but in another school it worked differently, but because it wasn't accounted for.
That could work for classroom level predictors, but not for school level. So that could be one reason. It could just be that they didn't collect any information that was relevant that predicted the outcome. But does that mean that you're okay to just go back to single level analysis? No, what that means is that if you have level 2 and level 3 variability in this case, if you have mean differences across classrooms and across schools, you have to put those mean differences in the model even if you don't know why they're there. Just because you don't know why they're there doesn't mean they're not there anymore. So we would have to put classes and schools as fixed effects or leave them in the model and just not have any predictors at those levels. That's fine too, but we gotta care. You can't go back to single level analysis if you have group differences. Gotta care.
So Lisa,
Yeah.
I have a question about this. So the difference between those two, except for the research question that we are interested in, I'm wondering whether, so if I go for the first choice, I only put the mean differences into the model, but I do not explain it because I can't. And for the second one, I can know how much variance there are for the level 2, but for the model 1, like the first model, I cannot tell that. I can only tell the mean differences, but not the variance across groups.
Yes, sort of. So yes, if you put in, let's say that you put in you have a single level model and you put in group as a predictor, you can see what the R-square is. So you can sort of work backwards to say how much group level variance would have been there that your fixed effects accounted for. But yeah, you're right, then you're stuck. Because you can't put in any group level information because you've already saturated all the group differences with the ID variable. So you've described the differences, you haven't explained them.
Follow-up question.
Please.
So if you do the first option and just put the school ID or something to capture that, that means that you can't, so if you are interested in, say, how school level free lunch.
Can't do it. Can't do it. Yeah.
I've been doing that.
Were you doing it with this one? Okay, yeah, so you can do it with this. What's happening is that behind the scenes, it's then taking the residuals and fixed effecting those, essentially. It's subtracting group mean differences out of the residuals to correct the standard errors. But you're not, in that approach, you're not able to quantify how much variation across schools is remaining after controlling for fixed free lunch and whatnot. So if that is a focus of your research, I would encourage you to come to random effects side. Another thing that probably goes up here in this first category is, what's it called? Generalized estimating equations, GEE models. That tends to show up in a longitudinal context where they're just sort of controlling for person dependency. That's analogous to this where you're not quantifying differences, you're just trying to control for them in the model. So we're staying down here in random effects land, that's where we're headed. So let's look at a couple examples here, some theoretical and then with software and data. So let's start with level 2 predictors, group level things in this case. So for instance, if I have level 1 students as my persons P, nested in level 2 schools as my group G, and I want to know whether or not math outcomes are different between public and private schools, and whether or not math outcomes are different as a function of school size. I can do that. So level 2 predictors are, the definition of those is that they are constant over persons from the same group. So that means level 2 predictors have to have what kind of intraclass correlation? Zero or 1? Let's go back.
Wait, if they were 1, wouldn't that mean everyone was the same? Isn't that what you said earlier?
Here's the formula. So level 2 predictors have what as an intraclass correlation? So continuing that thought, Kayla? What do you think? 50-50 shot. 0 or 1?
1.
Gotta vote for 1? Anyone else want to vote for 1? Abstain?
I think it's 1. If they're constant from the same, over persons,
Mhm.
every person is basically the same.
Mm-hmm.
And then that's the scenario you have one person representing the group, right?
Yes. Your vote is 1?
Yeah.
Final answer?
Yeah.
Yes. Yes, 1. So between groups over between versus within. So if I have something like whether my school is private or public, right? If all the kids from the same school go to the same school and that school is of one kind, there is no within school difference. So the definition of level 2 predictors, group level predictors, is that they have an intraclass correlation of 1. If you're ever handed a data set and you're not sure, run an empty model and you'll figure out whether or not there is school level variance. If not, then you can be, or if there's no residual variance, then you can be assured that you have a level 2 predictor. So yeah, level 2 predictors, school level things, between group things in this context. Let me find, where was I? Here I am. So leaving the level 1 model empty for now, I have math as my student level outcome in this hypothetical example, per person per group, is a function of a group specific intercept plus E, which is how far off I am from my group's intercept. Now how does each group get its own intercept? Well, we come down here. The first model that I would estimate is the empty model with no predictors, just to find out how much school variance there is to be had. So gamma 0, 0, this should be red. Let me fix that real quick. I want that one. Nope, wrong red. There we go. Thank you. That one, gamma 0, 0, is the mean math of the group means. So the average school mean math. U then is how far off each school's mean is from the grand mean. If I then examine those predictors in a model, it might look like this. So now we start to see the logic of the subscripts. In the gammas, and in everything, the first subscript refers to the level 1 model, the second subscript refers to the level 2 model. So for instance, in the equation for beta 0, because what we're talking about is beta 0, the first term in this entire equation for beta 0 is a 0. Because all of these things go with beta 0 as the thing they're predicting. Within the level 2 equation for beta 0, the second subscript indexes which predictor of that beta it is. So O is like the intercept of the equation. In this case, it is the fixed intercept. Gamma O1 for private is the first predictor of beta 0. Gamma O2 is the second predictor of beta 0, and then I put in their interaction as the third predictor of beta 0. If I had any other level 2 variables, what would their subscripts be? Not a trick. What comes after 3? 4, yes. Then 5, right? Now the difference then in interpretation has to do with what U0 means. This is now the idea of variance left over. So each school's mean is now a linear function of whether it's public versus private and how big it is. U0 then is how far off the real school's mean is from the one that's predicted based on type and size. So you can think of U0 as all the reasons why schools still differ from each other in their mean math after controlling for private and size. So because this becomes variance left over as an idea, some textbooks use the term level 2 residual. I'm going to try not to do that to you because in my world it's level 1 residual and level 2 random intercept. The difference is what the level 2 random intercept means. In a model with no level 2 predictors, it's all the group level mean variance. After you put in predictors, it's group level mean variance left over. Okay, how are we doing? Okay. Yeah, question?
Let's go back the question a few minutes ago you talked about. So if you tell that U0G is that if that is essentially equal to 0, then
If it's equal to 0?
yeah, so which means we have pretty good data in the level 2.
In the level 2, yeah. Can this go to 0? Is that your question?
Yeah, I mean if that goes to 0, then why can't we just use a simple regression?
Then in theory you could. However, the question would be what happens to these effects, like whether or not their standard errors would be correct or not. It's because they're explaining the difference.
Mm-hmm.
So if it goes to truly 0, then I think it'd be okay. If it goes to non-significant, but not 0, that's where the problem comes in.
Okay.
I would leave it in, just to cover your bases. But yeah, in theory, let's say that we estimate an empty model in which we have an intraclass correlation of 0.2. What would that mean in this context? %20 of the math variance is due to schools, mean differences across schools. So from a variance explained perspective, what would my R-square be for the overall model in the situation he's talking about where this goes to 0? %20. So if there's 20% school level variance, by putting in school level predictors, the absolute best I could do is explain 20% of the math variation. That's my upper limit. Because how big my school is can't explain why I might do better than my classmate. That's untouchable. That's E-variance. It's a different category. So what would each of these things mean in this model? Well, gamma 0, 0 would be my fixed intercept. As before, intercepts are conditional on the 0 values of all the predictors. So this would be expected math for a student from a public school of size 0, so grand mean in this case if I've centered at the mean. Gamma 01, given the interaction term, is the difference between public and private, specifically for 0-size schools. Gamma O2 is the difference per unit size for public schools. And then gamma O3 we can talk about as how the difference between public and private varies by size, or how the effective size varies by public versus private. We could compute a omnibus test of all three fixed effects to see whether or not the total amount of variance in the random intercept that's been explained is significant. And we could look at the significance of the wall test for each one of these as well. Just the same as usual. And then the level 2 part is, as I said before, random intercept is how far off you still are from your school mean and the one that's predicted by the model. Level 1 residual is still the deviation of each student's math from the predicted school's mean, whatever that happens to be based on their private and their size and their random intercept. Effect size. So here's where it gets fun. There's no longer a single R square. There's a couple different ways that you can convey effect size in multi-level models. There's more being developed as I speak. An easy way is just to compute D's and R's from your results. So every test that you see for T or F, you can compute back into a D or an R. Here's the formulas to do that. They can work with any type of model, not just multi-level. So I've done this for power analysis and for results reporting types of things. A more, let's see, how to phrase this. A more comprehensive measure that describes the overall model as opposed to each thing that goes into it is R square. And in this case, we have at least a couple different kinds. Pseudo R square is a new concept. This is the idea of how much variance you've explained per variance component, or as I would say, per pile. So we have the level 1 E pile, the level 2 U pile. Each of those can be reduced by predictors of its own kind. So in this case, if I'm talking about adding level 2 predictors of my intercept only, the variance that they should reduce is this level 2 random intercept variance. E variance at level 1 should be unchanged. Because E variance is why are you different than everyone else in your school? That can't be explained by what kind of school you go to, because everyone else in your school goes to that same kind. So I can compute how much variance has been reduced by adding my fixed effect in. So this general formula works for any kind of variance component. It's what it was minus what it is over what it was. Proportion reduction in error, as it's known in other contexts. The reason that it's called pseudo is that this can go negative real easily. Variance components are not often stable, particularly in unbalanced data. They can shift around a little bit, and if you add a really non-significant predictor into a model, it can actually make your variance go up, not down. It's also a sign of model misspecification if your variance goes up and not down. These problems can be overcome with a slightly different version of R square that uses model implied total variance. This is a new article that I think is going to be pretty important heading forward. They have a follow-up that I just accepted as an editor at MBR, but I put it in your reading list so that you can see this. They have an R square package in R that they made to go with this, by the way, so you can download that and have it calculate things. So pseudo R square we're sticking with because the calculations are simple. This model implied total variance is a way to avoid the fact that they sometimes go negative. The other thing that you can do is to put the piles back together to refer to total R square. And this is the idea of how well your model works to predict any single outcome. So we've been doing this actually in the handouts examples you've seen so far. If you ask the program to calculate the outcome that is predicted by the model's fixed effects, it's called y hat a lot of the time, or predict xb in stata. You correlate that column of predicted outcomes with your real one, square that correlation, that's R square. So total R square is a way of saying overall, across all the level 2 variance and level 1 variance, how much total variance did your predictors account for? So it's putting it all back together again to make a comprehensive measure of effect size. So these are complementary ways of describing things, per pile and overall. So for example, let's say that my model came up with the following values. I have a level 1 residual variance from the empty means model of 8, level 2 random intercept variance from the empty means model of 2. So that gives me an intraclass correlation of level 2 over total of 0.2. So 20% of all the variation in my outcome is because some schools are higher on average than others. Cool. Now let's say that I put in my predictors, private, size, and their interaction, which are all level 2 variables. So they have explained part of the level 2 variance. Let's say that they get half of it. So the level 2 variance used to be 2. Let's say it's 1 after putting in my 3 fixed effects. Level 1 variance stays at 8 because school predictors cannot explain person-level information. So how would I convey an effect size for this? Well, pseudo R square, what it was minus what it is over what it was 2, it's 1 now, over what it was, 50%. So that sounds like a lot, right? An R square of 50%, have you ever seen that in real data? Not really, not unless it's fake real data, right? So that means that of the 20% of the variance that was due to school mean differences, we got half of that 20%. Half of the 20%. So it's a proportion of a portion. To put it back together again, you can approximate total R square by doing the multiplication. It's 20% of the 50%, or 50% of the 20%. I learned a long time ago that when you hear the word of in a word problem, what are you supposed to do? Multiply, right? So 0.5 times 0.2 is 0.1. So I got 50% of the 20%. That works out to be 10% of the total. So total R square is 10%. Of all the variation in math, I have 10% of it that is due to school characteristics of size and type. Now there's a sense in which that's not fair, right? Because logically speaking, if only 20% is possible to be attributed to school level differences, that should be kind of the new target, right? So I have 50% of what I could have possibly gotten with my school level predictors. So there's not a right answer as to what to report. I tend to do both because they're complementary pieces of information. In models where you have a whole lot of variance components and it gets really painful to try and keep track of them all, I punt and just go with total R square. Total R square is also used in situations in which you have the same construct being measured at level 2 and level 1. So for instance, if I had student free lunch status and I also had rates of free lunch across a school, and I put both variables into the model at the same time, then total R square could tell me how much of my total variation is due to any kind of free lunch, putting them back together again. So it's imperative to explain what kind of R square you're using and how you calculated it, because there's like literally dozens that are floating out there that people call R square, and they each mean something different by it. So this is, for this reason, by the way, in mixed, have you noticed there's no R square on your output in the mixed examples we've seen? Someone asked me that. I think it was you, Elmira. I think you asked me this last week, that aren't we just doing regression? Like, why aren't we using reg, right, or regress? Because I wanted you to get used to mixed is my answer. But yeah, the reason that mixed doesn't give you an R square, because it's like, I don't know which one you want. There's 8,000 of them. Whereas in regression, there's only one. So it's happy to give it to you. So I've written SAS macro programs that do total R square and do pseudo R square. Total R square is also real easy to get in Stata. I did some searching on the internet to see if I could find some Stata macros for pseudo R square, and I didn't find any that were using mixed instead of XT mixed. So maybe you could make one and get famous. I don't know. for those of you who want to do that. There's all kinds of stuff floating out there in R too, I'm sure. So intermediate summary then. So modeling process for multi-level data always starts with empty model. You got to figure out if you have school level differences or group level differences before you can go and explain them. You want to quantify how much you have with intraclass correlation. Testing groups as a random effect then allows us to put in group level predictors and see how much of the group of variance we can explain. And we can describe that in a multitude of different ways. All right. You want to see an example for a few minutes anyway? Why not? So these come from fake real data. Well, they're supposed to be real data because they're from your textbook, but I have my doubts. Let's put it that way. So this is data from Snyder's and Bosker, a sample of 3,305 students from 178 schools. So this is example 3A that I just posted. They have language outcomes from a pre-test and from a post-test, and they used post-test in the book. So I grabbed some of their school level variables as well as student level variables we'll look at next time. Homework amount is what it seems to be, although it looks like a Likert scale average of some kind, goes from 1 to 5. Denomination, which is school type that's categorical, and nowhere on their website or in the entire book could I find what that means. So I'm just going to call it type 1, type 2, and type 3, because whatever. I wanted you to have a categorical variable to play with, so whether or not the classes are mixed grade is the other school level variable that we'll have here. So doing a whole lot of data pre-processing here to get descriptive information because this was a student level data set. So here's the SAS code importing. I saved it as an Excel file so that we could look at the data easily, labeling things here and subsetting the data. Side note, I am subsetting this data set to be complete for all the variables to be examined in this example. Why I have to do that? Because multi-level models do not handle missing data. Any row that is incomplete is not included in the analysis, whether it's a predictor or the outcome. We'll talk later in the semester about what to do with missing data per se, but it's not solved in any way, shape, or form. So if you want to have the same sample across analyses, you got to subset it to begin with to keep everybody in. I also kicked out denominations 4 and 5 because there were only a couple of schools that met that category. 2 of the variables for student level were measures of IQ that I standardized. We can forgo that for right now. I created a school level data set so I could get descriptive level statistics. I did that in SAS with proc means by school, where I outputted a new data set and saved the mean of these things. Created dummy codes for a denomination and centered the school predictors. Homework was the only one that wasn't near 0, so I centered that at 2, which was near the mean. And then there's some descriptive stuff. In Stata, a lot of the same stuff, computed row miss so I could kick out those. In Stata, it's much easier to make school level means. That's an eGen. So within the same data set, I was able to make school level means to summarize things. Did the contrast coding and the same as before, and centered and labeled all of that. The one thing that was tricky that I had to figure out actually to do the website for my book was this idea of preserve and collapse and restore. Have you seen this before, Stata people? No? Something new? So Stata, as up to version 15 at least, only let you have one data set open in memory. So if I wanted to have a school level data set and get descriptives on it, I would have to shut down my student level data set, open the school one, get my stuff, shut it down, get the student one back. That's annoying. So I asked the Google, how do I avoid this problem? And found this. So it starts with the option preserve, which warns data that I'm going to want something back after I do something with it, and then collapse. So it takes my student level data and averages across rows from the same school for all of these variables. I was then able to run descriptive statistics, frequencies, means, and so forth on the school level data set. And then restore makes it go back to what it was, the student level. So student level is what remains in memory. The school level one is just temporarily there in order to spit some stuff out. So I thought that was a nifty trick. In SAS, I have two different data sets that are operating in memory at the same time, student level and school level, so I don't worry about that distinction. Okay. So here's some descriptives for the data. 3 different types of schools. Some of them are the use of mixed grades. And then here's some school level variables that we'll look at later. Sure.
When you say school level variables,
Mhm.
do you just mean that they all just had like a student ID on them, and then you like collapse them or like summarize them?
Some are like that, and some are truly school level. So what I ended up doing, so we'll talk about the student ones when we get to level 1. This is sort of in preparation for that. But like homework, this was a variable that was already school level. All students from the same school had the same value. And so that's a truly school level variable. Whereas I computed the mean across students and these other things, and it becomes school level at that point. But I also have the student level version of it too. Because what we're going to end up doing is using them both.
And that would just depend on how the data is already.
Mm-hmm. Yep. What I wanted to do was to be able to describe school differences in things that were school level as well as in things that become school level as part of the model, which like things that are collected at the student level are also going to be school level, just like the outcome and the predictors. Yep. All right. So, yeah. So looking at this language, let's look at these 2 rows right here. This is school mean language. Up here, this is original language across students, and this is original language minus the school's mean. So this is the brute force version of what the model's going to do for me. It's going to carve up language into how much of its total variation, this line right here, standard deviation of 8 and some change, is due to school mean differences, this one, versus within school differences. So to the extent that some schools have higher language on average, which in case you can see there clearly are differences here, some schools have average language as low as 23 and as high as 50, we need a multi-level model. And foreshadowing student level predictors, they have verbal IQ and performance IQ as student level predictors. These are the school averages in those. So when we get to level 1 predictors, that's where it gets tricky. Even though you're thinking of student level information as explaining student level math, to the extent that student level information is common across students from the same school, it becomes school level information as well. Thus the basis of your question, right? So to me, these are all level 2 variables, although only one of them was measured directly at level 2. So these 2 rows here are foreshadowing the idea that we're going to need to think about the multi-level aspect of our predictors as well as our outcomes. Sure.
So is that assuming everything is measured in X and Y? Like units and everything? Schools?
Yes.
Okay. Because I feel like that's something I'm running into, is like none of them are the same.
None of
So
them
I
are the
wouldn't
same.
even be able to do
Each
that.
school measures the construct differently.
Yeah.
Oh. Suck to be you.
Yeah.
Is there any commonality?
Yeah, there's just some things we can't use, like grades are even different.
Mm.
Some use like age rough, some use like standards,
Mm.
and there's really no way.
Yeah, you'd have to come up with some sort of within school standardization.
Yeah.
Like
Which doesn't even.
yeah.
Okay.
Well, like mean is 0, variance is 1. Like I give up, right? Like
Yeah.
you would center around whatever it happens to be for each, and try and it's like you'd have to somehow make the scale the same, but then you would lose the ability
Yeah.
to make those sorts of school comparisons. Yeah, and I'm sure you don't have any students who have like the same scale across multiple sources, right? You can't like link them back together.
You probably could, but we don't have access to it.
Okay. Yeah. So at most you could look at relative comparisons if you could get all the students onto the same within school scale, but you would lose this
Yeah.
aspect. So yeah, bummer. But that's reality.
Schools that do the school things.
Yeah, I mean, some sort of subset analysis, and then you could have a nested effect for those schools that you are able to do. You might also throw that in as a school level predictor, which system they use. Because like if you have A through F versus like percentage, so that was like one thing. I went to one high school where like they took your percent in the class as your grade, like that was what went into your GPA. And so they had like down to like, the valedictorian was like an average of 96.33974, right? And then like the next person was 33973 versus like the other high school is like, 50 of us have 4.0s, hooray! Like, so if there's more measurement precision, that might allow for stronger effects potentially, and that might be something to think about. So, hooray, we're all done! We're all valedictorians in life, aren't we? Does that even matter now? No. All right, so we get to dig back into this example next time. Let me know if you have any questions or need anything. Office hours start now. See y'all later.